Hello, assalamu alaikum, namaste, vanakkam. How are you, my chums? What's going on? So, we are back with a new topic which is called as thermal expansion. See, thermal expansion is basically one of the most important topic in the perspective of NEET or mains. See, advanced don't play with this, but he will use this concept to make some advanced question. Okay, so from here you can expect more NEET questions and more mains questions. So let's get started without wasting any time. For example, see, if you have any metal, or let us say any metal is there this much. If you heat this metal, you know one thing, this metal expand. What is the amount of expansion? This kind of questions. Or else, for example, if you take any vessel, that vessel is full of water. If you raise the temperature, this water will boil and it will fall down outside. The amount of water fell down. Or else, you know, in ancient times we use pendulum clock. Now also we use like one clock which has pendulum. Now this pendulum clock at the summer time, it started showing some late time. We can say lagging in time. Because of what? What is that lagging in time? This kind of topics we are going to learn in this class. So without wasting any time, let's get started. Myself Toufeeqqneakk, and this is your beautiful and your lovable channel, Areal. Let's get started without wasting any time. Thermal expansion. Now basically, what is this thermal expansion? Before knowing thermal expansion, you must know one thing which you know. You must know one thing which you know. What is the thing? The thing is, every solid, liquid or gas is made up of molecules. Correct? Molecules, molecules, molecules. And you know that in solid, molecules are tightly packed. In liquid, molecules are not tightly packed. But okay, it is packed but not tightly. In gases, molecules are free. Correct? Molecules are free. Molecules are okay. Molecules are tightly packed. Now let's get started without wasting any time. Now first thing, that molecules, if you take any gas, any liquid or any solid, if you increase the temperature, what happens? See, if you increase the temperature, increasing the temperature, if you increase the temperature of solid or liquid, solid, liquid, gas, whatever, gas. That time, what happens now? If you increase the temperature, these molecules are there now inside this gas, liquid, glass. These molecules start increasing kinetic energy. For example, let us take gas which has loosely packed molecules. If you increase temperature, that molecules start moving very fast, random motion. Similarly, in liquid also, but in solid now, we will see some other kind of thing. See, gas, liquid, okay, it will expand, but in solid, some other thing. What is that other thing? Now, here, molecules are not full tightly packed. Molecules are full tightly packed. It can't move directly with kinetic energy. So, that time what happens, we will see. First of all, if you increase the temperature, this temperature cause increase in the kinetic energy. Okay now? Gases we can study very easily. Gases, it will increase because it is randomly moving. It can increase any direction. But what about this and this? Gas and liquid and solid. Now you know one thing, solid molecules are tightly packed. That time molecules can't move very easily. So molecules, what happened now? Molecules can't move very easily. So molecules start vibrating like this. Molecules start vibrating because you are heating temperature. Molecules are here, it will start vibrating. If it is gas, it will move. But it is solid, so it will start vibrating. So when you rise temperature, increase in kinetic energy, molecules increase kinetic energy. Now this kinetic energy increases the vibration in molecules, solid and liquid, or vibration in molecules. Now this vibration will increase. Now this vibration is increased. Again I am raising the temperature. Now vibration is increasing. At one point this vibration, what happens? See, vibration is more. It started colliding with neighbor molecules. Correct? When vibration started increasing, then it collides. Molecules, you can say like this. molecules start colliding with each other. Super, right? Super. Now, when molecules start colliding with each other, then what happens? See, molecules colliding, which means this molecule acting some force on this molecule acting some force on this molecule, which means force acting, which means here produce, stress will produce. So when they started collision, that time it produces thermal expansion takes place. It produces thermal stress will produce. Thermal stress will produce. Now once this thermal stress will produce, now see, it collide, force acting, stress producing, because of it produces stress, so thermal stress. Now this collision will make these molecules to move away. This collision will make these molecules to move away because energy will be more, so it will move away. Now if it is moving, then intermolecular distance is increasing. So thermal stress is producing, which leads to increase in intermolecular distance. If intermolecular distance is increased, now you are talking about only two molecules. If this kind of n number of molecules, all the intermolecular distance is increasing, then automatically here we can see expansion. That expansion is called as thermal expansion. Thermal expansion. It is like this. For your understanding, I will explain. See, there is one solid which has 4 molecules. Let's say which has 4 molecules. Now, when you rise the temperature, these molecules can't freely move because it is tightly packed. When you rise the temperature, it can't move because it is tightly packed. That time, what happens now? This start vibrating. This will start vibrating like this. It is like this. It will start vibrating. Like this, it will start vibrating. Now, if you increase more temperature, then this vibration will be more. Which causes collision. At one point. At this point collision, force will be more, so it will move away from each other with more speed or with more distance. Then it will produce increase in value. Okay, now very simple thing. It will produce increase in intermolecular distance. We are talking about 4. If you take n number of molecules, then more distance, more thermal expansion takes place. Okay, now small thing, take down first. Okay, fine, super. Now, let's get started with potential and intermolecular distance curve. Potential, sir, you said only kinetic energy. Now you are talking about potential. What is this going on? Ayyo. Don't worry, I will tell you what is this going on, why it is going on, and why it should be going on. Wow. Okay, whatever. My English is better than any British. Now, see, I will tell you one thing. If you take a solid, you know, here all the molecules are tightly packed. These molecules are not moving. It is a stationary, which means it is not moving, it is stationary, which means it has some potential energy in it. Correct? If something is stored, it has some potential energy. It is also not moving, it has potential energy, maximum potential energy. Now, when you give temperature, that time it starts moving, which means potential energy is converting. Potential energy is converted into kinetic energy. Correct? Kinetic energy. Now this potential energy, what happens? The potential energy started decreasing. Which means potential energy decreasing. Total energy, see, you know one thing, total energy is equals to potential energy plus kinetic energy. Now this molecules is at stationary, which means it has potential energy. Now I am increasing the temp, which means at the initial no kinetic energy. Initially no kinetic energy, which means this much, right? Because this will 0 at initial. Now you are rising temperature, which means if you are rising temperature, molecules vibrate, which means kinetic energy started producing. So then you are raising total energy, which leads to potential energy decrease plus kinetic energy increase. Very simple. So every point kinetic energy increases, potential energy decreases. Now this curve comes like this. If you take a small curve, see curve, okay. Now let us take here total energy, and here it is R. This R is equals to intermolecular distance. When intermolecular distance increasing. Now how this curve comes means, say at the initial potential energy, sorry, it is potential energy, let's take it as potential energy. At the initial potential energy is more because it is tightly packed. Potential energy is more. As you increase the distance, potential energy start decreasing. See, and at one point it again start increasing, but it can't increase more, so it will stop there only. This kind of curve you can see when you rise the temperature, because see, whenever you heat any metal, that metal first start expand, and you are still heating metal. That metal, if you are heating, it start expand. At one point it will again come less. See, it is this much. You are heating, it expand. It is a maximum expansion, and again it will cool for some time, and it will become there only. Like this, potential energy is decreasing. At one point, this is maximum decrease. Then again, it will start cooling. Okay, now this kind of thing happen. Are simple raw time saying now, if you heat any metal, first that metal will expand, more expansion. Okay, now more expansion. Then again, little it will cool and it will form stop. Okay, now this is the main thing. Okay, take down first. And one more thing I need to tell you. What is it now? If you increase the temperature, thermal expansion will increase more in gases. Thermal expansion, okay, where can I write here? Okay, see, if you increase temperature increase, then thermal expansion more in gases and less, or thermal expansion less in solid. Liquid stay in between both of these. Now why this is more, why this is less, means in this molecules are tightly packed, which means intermolecular force is more. In this, molecules are loosely packed, which means intermolecular force is very less. See here, why means, let us take reason also. Here reason, intermolecular force is more. Here, intermolecular force is less because intermolecular force is less because molecules are far away from each other. Now what force will be less, right? In this, molecules are near to each other, force will be more, right? Okay, now that's why thermal expansion will be more in gases than in solids. Okay, now liquid will stay in between both of these. Okay, fine, take down first. Now, okay. Happy hour say, अपने प्यार से ढूंढेगी सारी दुनिया इंतजार से, happy hour से. Okay, students. Now let us get into one of the most and good topic, linear expansion, or you can say linear expansion only. Linear expansion, you can say linear expansion only. So next topic is which is linear expansion. Now what is this linear expansion and why this linear expansion we'll going to study. Now linear expansion means, see, linear expansion means that the increase in value or increase in only one dimension. See, if it is there, this length increase like this, like only one dimension, it is called as linear expansion. Now for example, let me take one small rod. Okay, this is one small rod of length, let us say L. Now, if I heat this, then this rod will increase some distance. This rod will increase, then that increase in length will be like this. It is normal. Like now it increases, let's say this much. It increases, let's say this much length. Because of heating, this increases to this much, which means overall length, what I am getting, overall length is this one, correct? Overall length is this one, whose length is like dash is equal to, let us say L plus root dou L, correct? Final length, whose, this become like your features dark. Alright. Now this final length, which is equal to this plus this, correct? This plus this, final length, correct? Final length is equal to this plus this, correct? Now how we know how much increase and what is the value of this? Now very simple. See, this expansion is there, which we call linear expansion. This linear expansion or due to heating or increase in temperature, the increase in this length depend on some factor. For example, see, this increase in your length is depend on your temperature, change in temperature, correct? And you know one more thing, one object is this much, the increase in length will be small. Now one object is this much, then increase in length will be more, which means if you increase the object, which means if you are increasing the molecules, then increase in length will be more, right? So which means it depend on length also. Somewhere this depend on length also. So can I write like this? Like if it is more, then this will more. If it is less, then this will less. Okay. Now if I write all this both together, then can I write like this? Change in length is directly proportional to length initial and temperature, change in temperature. Now, if I remove this proportionality constant, I will get one constant term which is alpha L dou T. Alpha L dou T. Now, this alpha is called as linear expansion, coefficient of linear expansion. This alpha, see, this alpha is called as coefficient of linear expansion, and this is constant. This is one constant term, and I will tell you one basic thing. I will tell you one good thing. This linear expansion is there. Now this coefficient of linear expansion, basically it is, we take it is constant, but practically it is not constant. Theoretical value is constant, but practical value is not constant in real life. But as for your calculation, we take it as constant only. Now it is change in length, which means I am saying this much. Now if I want overall length, final length, this is change in length. Remember, this is change in length. If I want overall length, then what I will do now? What I will do if I want overall length? See, very simple. I want overall length, which means I want this one dash, which is equals to, correct? Super. Now I can write this as like this. Correct. Now if I remove L and L outside, then I will get final expression as this one, right? Once again, I will get final expression as is equals to, remove this L and S constant, which is like 1 plus alright, see, this is your final length. Final length is equal to initial length bracket 1 plus alpha dou T. Okay, this is your final length. This is your change in length. Now remember this formula, because this formula you will use everywhere. If you remember this chapter is over, which means thermal expansion is over. If you remember this, thermal expansion is over. I bet. Okay, take it first. Okay, then come on. Now this is important formula. I said take note. Now I will tell you some basic things about this formula and how it works. Works, anything. I just know work energy power. That's all. Right. Now, for example, see, you know formula is this much. Change in length is equals to L alpha dou T, temperature, change in temperature. Final length is equals to initial length 1 plus alpha dou T. Correct? Now come to this one small example. See, if I have one radius like this, one metal which is like this, whose initial radius is R. Now because of heating, it turns to more. It turns more, which means it turns to R plus dou of R. R plus dou of R. Now here also you will write same thing. Here also you will do same thing. Change in radius is equals to initial radius alpha dou T and final radius is equals to initial radius plus 1 plus alpha dou T. Okay, like these things of questions you can be asked. Now one more thing. See here. One more thing. For example, if I take one rod which is curved like this, one rod which is curved like this. Now I am taking this point and this point. If I take these 2 points A and B, let us say. Now if I heat this, you know, if it is like this, if I am heating, it will expand. It will expand and it will become like this. Correct? Expand. It will expand. That time if it expand, then this length which is L, then what is change in this length? Which is equals to initial length plus change in length. Correct? Again you will do same thing. Here also change in length is equals to original length alpha dou T, or change in final length is equals to original length plus 1 plus alpha dou T. Okay, now, like this kind of things, be prepared. Very one formula, every method. I can ask this in n number of times. Okay, take down first. I will tell you one good thing. Good to great to, whatever I need to tell, I will tell. Okay. See, I know if you are feeling this is very slow, you can go with the 2x speed. 2x speed. Okay, now. Okay. Stress. See, next topic is stress in objects due to thermal expansion. Sir, stress. Sir, this we studied in last chapter, right? Yes. Here also it came. Yes, it will come everywhere. Now, how this stress? Now, see, I'll go to main topic. Now, if I take 2 clamps, which means we are used to clamps, and if I fix these clamps here, and on this clamp, if I take a small wire like this, okay, now clamps are fixed. This is fixed. And let's say this distance is L. Now, if I heat this, you know one thing, because this clamp is fixed, when I heat this, these molecules will add some force here to move. See, it is like this, a wire is like this. If you are heating, these molecules will add some force and it will start expanding, right? Expanding. Now, because this is fixed, it can't expand, so then molecules will hang like this. Fix. Now, molecules will start hanging like this, because it is fixed. If it is not fixed, then molecules will expand like this, or this string will expand like this string. But it is fixed, so it is expanding like this, or you can say force acting. Okay, now this will happen. Now here we can see change in length. Correct? Now here final length is L. So here it is equal to initial plus final. This is and here temperature is T. At this point temperature is T plus dou T. Correct? Because we are raising the temperature. Okay, fine, good. Now what I can say? Good thing. This thing. Now what is this force acting here? The force which making this to come down. This we need to calibrate. Now see, first thing, let us go with the main thing. Here, stress. What is the amount of stress here? See, stress is equals to force by area of cross section. Let us take this. Force here, force is acting. Here also force is acting. Area of cross section. And strain. Strain is equals to change in length divided by original length. Here L, here change in length is d of L. Here L, here change in length is d of L. Correct? It is original only. It is changing. This must change. Let's say this is d of L. Original length, change in length is d of L. Okay, now if I solve this, then what I will get? Let us see. Strain is equals to. Can I write this as dou L dou alpha T? Correct. No, it's not correct. Dou alpha dou T into L. Can I write like this? See, change in length. I can write correct now. Change in length is equal to length into alpha into dou T. Correct, right? Now here L cancel. Then strain will remain as alpha A T. Correct. Strain will remain as alpha A T. Now I know one thing. Young's modulus, which is equals to stress divided by strain. Now this stress is equals to force upon displacement divided by strain is equals to alpha A T. Alpha dou T. Now this Y is equals to F into S alpha dou T. Now overall force acting here, which is equals to Y alpha S A T. And here Y is Young's modulus, depends on material. Alpha is cross section of linear cross section. So coefficient of linear expansion, and S is here area of cross section. This is area of cross section, which is force into displacement. Force acting in area of cross section. Correct. See, when I heat this, when this fixing this two hooks, if I heat this metal or if I heat this string will act forces to expand, but because it is fixed, it can't expand, so it will expand material like this. Now what is this force acting is this much. Now how it takes stress is equals to force by area of cross section. Stress is equal to force by this area of cross section. Now strain is change in length divided by original length. So Young's modulus with stress by strain F by S divided by dou. Correct? Here I am writing this as this. Then if I do finally I get force as YAS dt. Okay, sir, this is very critical to remember. Array, don't remember. See, I will give you one. You are not going to do this all in exam, right? You are just doing this to your understanding. No, you just want force. See this one. This is why I write like this. Y alpha S into dou T. S dou T. S T. S T. See, it is YAS. S T. I know YES, right? But I say YAS. S T. YAS. But you know what do you mean by F? See, yes, you must know. Just remember like this. YAS T. S T. S T. S T. YAS T. And whenever they ask force is equals to S T, which is Y alpha S dou T. Remember this S T when they are doing problems. I will ask more time. S T. Okay. Okay, fine. Take down fast. I'll tell you one more thing. Alright. Good. Alright, fine. Okay. Now, same thing. If I take one metal. Okay, now, see, I am taking one metal. And fixing it to wall. It is like this. Two walls are there. I am keeping here one metal. I am keeping like this. Two walls are there. One metal I am keeping like this. Now this wall is fixed. Metal is middle. Okay. Now if I heat this temperature, if I heat from downside, which means this started increasing length. because of thermal expansion. That time this metal is there now, it will go inside the wall. See, it is like this. It is normal. It is normal. When I give some, it is normal. When I give some heat, then this metal started increasing length, which means it is going inside. See, it go inside the wall like this. Inside the wall, both the direction. It will go inside the wall, both the direction. Which means it acts some normal force here. Contact force which is normal. Contact force which is normal. Normal. Correct? Normal. Here, in that we saw force. In that we are seeing normal force. Same again everything you write. But here, this force will become normal force. Area of cross section is this much. Area of cross section this much. And again you will get to same formula. Here you will find normal which is equals to YAS. ST. ST. Okay, now fine. Take down first. Take down first. Okay, student. Over and out, over and out, over and out. Alright, fine. Now let us come to main thing. Variation in time period of pendulum clock. Sorry. Alright, fine. Variation of time period in pendulum clock due to thermal expansion. Variation of time period in thermal clock due to thermal expansion. Now you know you have seen in your home there is a clock which is pendulum or tick tick. See, after 1 hour it will be like ting 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 every 1 hour, like that clock. Now that clock, see, that clock is made up of metal. Now when it is summer time, that metal will increase. That it is summer time, temperature increase, which means that this okay. If it is like this pendulum, it is more ting 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 ting. Now when it is summer time, this temperature is increased, which means this length of pendulum is increased. Now if length of pendulum is increased, then it will cover more distance in less time. Correct? Here it will cover more distance in more time. Less distance in less time, more distance in more time. But here, due to increase in length, then it will cover slowly, it will move. Correct? It will move slowly means it is losing some time. That losing time only we need to find here. See, what I am saying is very simple. At summer time, pendulum clock loses some time or lags some time because it expands. That lag of time only we need to find. Now let us get started. You know pendulum time period is T is equals to 2 pi by L into G. 1 second. See, this 1 hour class, in 1 hour class I can't do much thing. Guys, if you are comfortable with the 2 hour class, let me know. Okay, 2 pi by T. It is initial time period. Now because of heating, let us say this time period has increased to T dash. Now then if temperature is increased, it is a temperature T. It is a temperature T plus dou T. If temperature increase, time period increase and length also increase. Okay, now length also increase. Now I know I can write L dash as L 1 plus A dou T, change in temperature divided by gravitation. Now this one I can write like this, dou T into Lg into 1 plus alpha dou t. Yes, I can write like this. Alpha dou t. Now what happens? All this term is equals to t. See, t. So what I can do? I can write this term as t dash is equals to t dash is equal to t square root of 1 plus alpha dou t. Now if I remove square root, then I will get as 1 plus alpha dou t into 1 by 2. Now it is in the form of binomial. Binomial, you know, 1 plus x to the power of n is equals to 1 plus n of x. Binomial theorem. Now if I apply this one here, then I will get as t dash is equal to t into 1 plus 1 by 2 alpha dou t. Correct? Alpha dou t. Now if I multiply inside, then I will get t is equal to t plus alpha dou t into d of t. Correct? Now it is the new timing. It is new timing. Okay. Now if I want change in time, then if I will send this here, then I will get 2 alpha t into t, which is called as change in temperature. Sorry, change in time. See, it is change in time. It is change in time. Okay, for your convenience, let us take it as small t. Okay, let us take it as small t. Then it will be very nice for you to understand. Okay, if I take it as small t, then you can understand very easily, correct? Because temperature you will get confused, correct? So right, now I think it is clear. Alpha t into dou t. It is change in time, or you can say loss in time. Change in time. Okay, loss in time. Okay, this is how time we calculate. Okay, take down first, please. Take down first. This is how time we used to calculate. Or change in, you can say change in period of oscillation can be given. This we can say change in period of oscillation. This we can say change in period. This what? Time only, right? Period of oscillation. Change in period of oscillation. Take down first. This change in period of oscillation. Or you can even say fractional change in time. Fractional change in time. See, I can even write this as like this. Okay, overall. Okay, fine. See, I can even write this as we can say this as fractional change in time. Okay, now change in time, fractional change in time, change in period of oscillation, all are same. You just understand there is change in time. Okay, fine. Take down first. Okay, fine. Now let us go to next segment. First, quick, guys. See, I want you to type in comment. I know this class is very useful, but I know one more thing. 1 hour class, literally, I can't do much thing because already I think it is more time. So if you are comfortable with the 2 hours every day, then please make a comment. No. Okay, fine. Now next segment, what I can say. Before the segment, I will tell you one simple story. See, one simple story now. When I was reading 11th and 12th, I had no one to say about me like mains is there or neet is there, because we are from low, we can say not good so-called town. But for that we made mistakes. You don't make these mistakes, you read very well. It's a very boring story, I also know, but adjust. Now, see, next one is volumetric expansion. Right. Before this, you take areal expansion. Now, what is this areal expansion? Areal expansion, it is like this. Now, if you have any small object which has area length L and let's say breadth as B. Now because of heat, this has changed to this length is changed to this much. Let us say, correct? This changed to this much because of it. Now new length is old length and it is change in length. It is new old breadth. It is change in breadth. Correct? Now if I write all my formulas for this one, here I can write like this. What I can write? See, first change in L is equals to L plus 1 plus alpha dou T. Correct? Alpha dou T. Now here also again change in breadth. Change in breadth is equals to original breadth plus 1 plus alpha dou T. Correct? Fine. Now it is length into breadth. Correct? Now can I take area dash is equals to area change. Here area A, here area change is A dash. So area A is equals to, I can take length into breadth. Correct? Now if I substitute this 2 here, then I will get L into 1 plus alpha dou T and B into 1 plus alpha dou T. Correct? I can write this as length into breadth into 1 plus 2 times of alpha dou T. Correct? Oh, sorry, not 2 times. It will become square, right? Sorry for inconvenience. 1 plus alpha dou T whole square. Now here length into breadth, which is called again as area, and again if I apply here binomial theorem, then I will get as 2 times of alpha into change in temperature. Change in temperature. See, this is change in temperature. Sorry, I am writing mix up. Please, I will use this same as capital T. Capital T, capital T, capital T, capital T, capital T. Change in temperature. This is final area. Now this 2 alpha we can write as beta. Okay, now then area change in area to original area plus 1 plus beta into change in temperature. This is your final expression for area. Now what is this beta? Now beta is a coefficient of areal expansion. Beta is a coefficient of areal expansion. Okay, now same thing. Take down first. Now same way we do for volumetric expansion. Same way we do for volumetric expansion. If I do for volumetric expansion, now again here if I do for say this is over, please take down first. Fine. If I do for volumetric expansion, one thing I will have Q. If I do for volumetric expansion, I will have Q. Correct? Q. This Q will increase to this Q. Length is increased, breadth is increased. Here you will find one more length into breadth to height. Height is increased, which is H is. Okay. So why we are taking alpha? Because we are saying that it is increasing only one dimension. It is increasing only one dimension, so we are taking alpha. And here it will come as one more. And here we will get here as one more H into 1 plus alpha into dou T. And here we will get one more, which is H. And here we will get as 3Q. Then here this will become 3. Then this will become your volume, and this will become your volume, final volume. Then again here we will write as V, and here we will write as V. Then this will become gamma. This will become gamma, and this gamma is called as coefficient of volumetric expansion. Coefficient of volumetric expansion. Take down first. Oh yeah, fine. Okay. Come on, let us study one more topic, which is variation of density. See, when I increase this thermal expansion, what is the variation of density? We will see. For example, if any object has initial density, this volume V, okay, at temperature T, Now, if I rise temperature, then you know, and mass is m, which is constant. Mass is constant, right? Mass is constant. For any object, mass is constant. If you hit temperature, it will density is this much, and it is V1 value, temperature is T. And if I increase this temperature into dou T, my value will increase to V2, and my density will increase to this. Correct? Now, this change in density I want, because first initial density, density is into mass into value V1. This we know. Now, I want change in next this density. Now, if I want this density, then what I will do, which is very simple, mass into value. Correct? It is final value. We can say it is final value. And you know one thing, final value is equals to initial value into 1 plus gamma into dou T. Correct? Initial value is equal to 1 plus gamma into dou T. Now, if I substitute here, density or final density to mass into initial value plus 1 plus dou into T. Correct? Gamma, let us say initial. Okay. Now, if I substitute mass value from this, mass is equals to dou 1 into V1. Here if I substitute, then here it is equals to density into 1, initial, then initial into 1 plus sigma into dou T, then this will cancel. Then density of the molecule or density of that particle or density of the object will become density is equals to density of initial divided by, or density at first divided by 1 plus sigma into dou T. Okay. Now for this, even I can even write this as like this. Minus 1. So if I substitute again, binomial theorem. If I substitute binomial theorem, then I will get as like this. Remember this. Only one formula we are using everywhere. Right? Only one formula we are using everywhere. This is how density is varying. Take note first. Density is varying. Okay, fine. Now, next segment is thermal expansion of liquid. Sir, how and what is this? See, for example, if I take one container of this liter, and this container, I am filling, this container has some value V. Okay, now same volume of liquid I am filling inside the container. Sir, why you are filling? My dish I will fill. Physics will fill everything. Because if you have full only, then you will understand how much it is changed. See, if you have this much of water, then how you know it is up or down? If you have full, if it is up, it will fall down. Correct? So we will take full. Okay, now if one container whose volume is V, in that we are filling one liquid whose volume is V only. Now, see, container, 1 minute. This container has volume V only, and this liquid also V, which means it is exactly filled. Now, if I pass temperature, that time what it happen, how it will changes. See, very simple. Now, what we can do? See, first thing. Remember one thing, sigma of liquid is more than sigma of gas, more than sigma of container. See, when you heat any container full of water, first you will feel like container is becoming heat, right? First, if you switch on the stove, first container will become heat. If you touch the container, you will feel, it is heat. But water is not heat. Container is easy for some time. After that, water become heat. Water become boiling more than this container. Which means what? Container So coefficient is very less compared to liquid coefficient is more compared to container. First container will boil. First container will get heat. After that, liquid start getting heat, which is more than container. Okay, now, then, if I say this, I know one thing, more thing, volume change in container. Again, I can write like this: final value. Right. Now, if I want to change in container, if I say change in container value, you know one thing: initial container, which is equals to and psi into dou t, and for liquid also same, initial value psi into dou t. Correct? Now if I want to know change in value, overall change in value, then change in value is equals to, because dou sign is more for liquid, we'll write liquid first, then container. Now if I substitute all these values, then I will get fine. I will get like this: L sigma dou t minus V of C sigma dou t. It is value. Okay. Now see, I can take like this. I can check. Hey, 1 second. There is a small mistake I made, because container value and both volume is same, right? Container value and both volume is same. Container value and liquid volume is same. Correct? Container value and liquid volume is same. Then why I will tell this? How stupid I am. From here, change it. Container value is same, which is VV. Both will be same only, right? Same only, right? Initial value same only, right? It is changing value. Now, if I write this, but here it is container, it is liquid. This is important. Okay, now first liquid minus value container into dou t. Container, it is C. Now V is common, dou t is common. Can I write it as like this? Yes, I can write it as. Now this term is called as apparent coefficient. Now if I want only apparent coefficient, then change in value divided by original value into change in temperature. Change in value into original value divided by change in temperature. So you can write like this: apparent coefficient equal to change in value divided by initial value. Initial value into change in temperature, dou t, change in temperature. Okay, now this is called as apparent coefficient. Take note first. Apparent coefficient of expansion. Apparent coefficient of expansion. Alright, right on. Then I will tell you one good thing. Okay, fine. Or right, now same thing, same experiment. Density of liquid at high temperature. See, same experiment. What is the density of temperature? It is when it is high temperature, when boiling or before boiling, high temperature. What is the density? You know one thing: density, final density is equals to initial divided by, you know this, 1 plus gamma of liquid container. Sorry. Here, dou t will come, right? Dou t. It is change in density. This we have already learned. Now we are using directly. Now after that, at one point, when container has some value, but finally liquid volume is becoming more, which means liquid will overflow, correct? Container volume is starting, it will increase, but it will stop. After that, liquid started rising, which means liquid volume increase. If liquid volume is increasing, which means liquid overflow. If it is overflowing, what amount of overflow? See, how much, or you can say mass of liquid overflow. See, mass we know, mass density, see, density is equals to mass by volume, correct? Change in density. If I say I want mass which is equals to, correct, fine, okay. Now that mass is equals to change in density, final density, which has, and volume just now we got it, volume which is equals to what we got just now, volume is equals to this one only, right? So stop doing breakdowns. Correct. Now if I substitute here, then I will get, this is my mass, this is my mass, this is my mass. Okay, now take down first. This is my mass. Okay, fine. Alright, that's it. Write down. Okay. Now, if I want this high temperature, see, I said high temperature density is much. Now, how to calculate that high temperature? If I want that high temperature, what I will do? See, if I want high temperature, then say I will use this one. I calculate high temperature. How means I can write like this, right? This one, then m plus m LC into dou T is equals to LC into dou T. Correct. Now, if I calculate this one, from this what I can do? I can send this side or yummy, so yummy. I want only this one, right? So what I will do? Okay, keep m here. Alright, now take the common m. Alright. Okay, what I want? Why? Today I had 2 samosas. See, this 2 samosas is blanking my mind. 2 samosas is blanking my mind. Ayyo. See, what happened now? Today while coming from school to my home, from institute to my home, I saw samosa, but I can't stop my temptation. As I am dieting, but also I can't stop temptation. I had 2. So because of that samosas, I am unable to do. Wow. I had samosa 2, because of that I am unable to do. Wow, such a talented person. Alright, now the change in temperature will be mass into density, initial, volume, and this one minus sigma into dou C. And you know one thing, sigma dou C is equals to sigma L minus sigma of container. This is the temperature, this is the maximum temperature. See, if you remember one, I know it is enough, but these things, see one thing, this only one is very hard. I know, remaining x, everything is fine. And this is purely for, this one. Take down first. Right, fine. there is one small thing remaining in this, which I will do now only. Say before, let me check how much time. Alright, fine. Sorry. Right, there is one small thing remaining. How to compare these three volumetrics, aerial and linear. These three we will compare in next class. Then after that we will start next full problems. Tomorrow we will discuss only problems. Today, so write one time, revise one time, fully revise these formulas, all volumetric, temperature and pendulum, and last this revise fully and understand why we are learning these topics and do it your best. Make the notes. Tomorrow your homework is revise all this, because tomorrow we are going to rock with the problems. Okay, now be ready, get ready. Till that, bye bye, take care, good night.